Good morning, dear student. Today we are going to discuss about the entropy. Okay, so entropy is a simple thing. Just we cannot measure it as a direct as a unit. So we cannot measure it simply. We can't measure it. We just say it is increase or decreases or it changes from one to or maximum to more or how is the disorder in the system. So, in first classes was introduced this system, this entropy, and in 1980, sorry, in 1884, that is classes had introduced this entropy, and entropy we cannot measure directly. We cannot experience the entropy, but we can just say entropy changes. Okay, so in terms of mathematically, I can define entropy, say the quantity of heat is absorbed by the system and at temperature T, then so dq is equal to T ds. Okay, dq is the small amount of heat absorbed by substance and T is the temperature during the reversible change. Okay, and this is the entropy. So this is the entropy. This is the entropy of the substance. The entropy cannot be directly measured. Okay, this entropy cannot be directly measured or cannot be experienced. So this cannot be measured or cannot be experienced like pressure, volume, and another things. Then this ds, this entropy is the fourth coordinate. It is the fourth coordinate of thermodynamics. Okay, it is a fourth thermodynamic coordinate. Okay, understand. So in order to know the concept, we are going to discuss the different isothermal compression and expansion. Previously we have already discussed this expansion and compression, adiabatic and isothermal. Okay, so we are going to consider, let's say, this is the pressure P and on this coordinate value V. So let's consider two adiabatic core. I'm considering two adiabatic core. Okay, this is two adiabatic core, A1 and A2, and I'm considering three isotherms. One isotherm, this is second isotherm, and this is the third isotherm. Okay, so at fourth isotherm temperature T1 and second T2, and this is T3. Okay, initially it will absorb heat Q1 and it will absorb heat Q2, and this is Q3. So this is point A, B, C, sorry, this is D, this is C, E, F. So to learn the concept, we are considering two adiabatic core and three isotherms. So according to theory of Carnot engines, we know that Q1 upon T1 is equal to Q2 upon T2. Okay, so this is the in the triangle. If you see that ABCD, this is the in that we get Q1 upon T1. Okay, Q1 upon T1, Q2 upon T2, and in similar this in this area, so in this cycle, in the first cycle, what we get in this cycle? In this cycle, we get Q2 upon T2, Q3 upon T3. So I can say that Q1 upon T1 is equal to Q2 upon T2, Q3 upon T3 is a constant. Okay. In general, if the quantity Q is amount of heat absorbed or rejected at temperature T in going from one adiabatic to another, then I can say that Qt is equal to constant, and this constant is the entropy. So this is called the entropy. This S is called entropy, and it changes between state changes between these two adiabat A1 and A2. Okay. So it is changes from one adiabat to another adiabat. So I can say that the entropy changes. Okay. If the adiabatic curves are very close, if I say if these two curves are very close within the state represented by two adiabatic curves, then if two curves are very close to each other and heat absorbed rejected as dq at temperature T, then I can say that ds is equal to dq upon T. Okay. In general, if entropy passing from one adiabatic curve to another adiabatic curve, so from S2 to S1, from say ds equal to draw name S1 S2 to S1 is equal to ds from 1 to 2 dq upon T. So this is the simple entropy. So it is clear that change in entropy depends only on first state to second state. It's not depend on this path. So it depends its initial state to final state. So it does not depend upon which path it is traveling. The entropy of the system increases when it absorbed and it decreases when it is rejected. Okay, so it is very important. You must write this. Entropy increases. Say entropy increases when it absorbs heat. Absorbs heat. And entropy, this entropy decreases when it rejects heat or it's give heat to the another body. So let's define the entropy here again. So dear students, let's define entropy. Then how we can define the entropy? If systems absorbs an infinitesimal quantity of heat, say absorbing it during a reversible isothermal process, the mean absolute temperature T, then entropy, I can say that entropy Ts equal to dq, dq upon T. When if a system absorbs infinite quantity of heat from heat dq from during a reversible isothermal process, and the mean absolute temperature T, then entropy is ds upon, so this is equal to dq upon dt. For adiabatic change, okay, for adiabatic change, what is adiabatic change? Adiabatic means no heat is flow. So I can say that dq is equal to 0. So in this case, ds is equal to dq upon dt must be 0. Okay. If it is isothermal, so there must be some quantity. For this reason, adiabatic curves are also called as isentropics. So adiabatic curves also called as isentropic isotropics. Okay, is also called as isotropics or a constant entropy curve. Let's consider SA and SB, two entropies from this state A and B. From which state? Say from this state to this state. Okay, so from the SA is the entropy of this curve, S2 is the entropy of this curve. Then we can represent like SA minus SB minus SA equal to from A to B df SB minus SA is equal to A to B dq by d. So this is the simple definition of entropy. The system absorbs an infinitesimal quantity of heat dq during a reversible isothermal process at temperature T, then entropy is a dq upon dt. Okay, this is the simple definition. This equation is difference of the entropy between two states. So SI unit of entropy. So unit of entropy is, so this is the SI unit and this is joule per degree Kelvin, not Kelvin. This is not, it is joule per Kelvin, or I can say that calories per degree Kelvin. Okay, so this is the unit of entropy. So you must be. Now we are going to discuss about the change in entropy during reversible process. So how the reversible processes happen during the and how the change in entropy during the reversible process. So we have already seen the Carnot reversible engine. Okay, it changes from A to B, C to D. Okay, this is for pressure P1, volume V1, P2, B2. This is for P3, B3, and this is for P4, E4. This is A, B, C, and D. That is for isothermal. This is for adiabatic. This is for isothermal compression. This is adiabatic compression. This is the isothermal expansion. We have already seen this heat engine. In case of entropy, so entropy in reversible process, how this we are going to discuss now. And we already learned this in Carnot engine, that is in reversible cycles. We have seen that. Now let's draw the pressure versus volume in, and we will discuss the change in entropy during reversible process. Okay, so change in entropy in reversible process. Reversible process. Okay, so let's draw pressure versus volume again. Pressure and volume. System changes from A to B. Okay, at temperature T1. Okay, so we have already seen that if we put the cylinder on the reservoir, then it accepts the heat and the gas isothermally compress. Sorry, isothermally expand. So here is gas is isothermally expanding. Okay, gas is isothermally expanding, and it is going to, so it is accept the heat Q1 at temperature T1. So it is isothermally expand. Okay, it is expand isothermally. When the system reaches at B, when we put the cylinder on the stand, then what happened? There is no heat is flowing between the source and the between the working substance and the stand. Then the gas is again adiabatically expand. So it is same Q1 P1, temperature is same. No heat is accepted or rejected. There is only at temperature T1 gas is expand, adiabatically expand. This is adiabatic and this is isothermal. Okay. Again, here gas is expanding, means that here its entropy is increases. Okay, increases Q1 and T1. Okay. This is the entropy. This is the entropy, increasing the entropy. But while there is no heat, heat is flowing, so there is a no change in the entropy. Again, if you see here, the gas is again isothermally compressed. Gas is isothermally compressed, and in that case, that heat is supplied to the sink. Then again, then there is a means it is rejecting to the heat or giving to the heat. Then that entropy is decreases. Okay, that is Q2 T2. So I must say decreases. Then in the complete cycle, the in complete cycle, this working substance regain its initial state using gas expand, thermally adiabatically expand, thermally compress, isothermally adiabatically compress. So within that cycles, then we get the entropy, that is Q1 upon T1 is equal to, sorry, minus Q2 upon T2. So for Carnot, we know that Q1 T1 is equal to Q2 by T2. Okay, so we can say that in the entropy, in case of entropy, Q1 upon T1 is equal to Q2 upon T2. If there is no change in entropy of substance, then it undergoes the reversible process. When the system is in a reversible process, so there is no change in the entropy. Okay, means working substance regains its original state. Now let's consider the source has lost quantity of heat Q1 and temperature T1. Q1 and temperature T1 is lost by source. Okay, lost it Q1 and T1 temperature. So then change in entropy of source, change in entropy of source change in entropy of source must be minus Q1 upon T1. Okay, the negative sign here indicate the loss in heat. Okay, now the absorbed heat by the source, that is at temperature T2 and heat Q2, that is must be Q2 upon T2, and then total entropy must be Q1 upon T1 minus Q2 upon T2, and that must be 0. Why that must be 0? Where when the I can say that the entropy of the whole system remains constant in reversible cycle. So this must be very important. What it says, the entropy of the whole system remains constant. Means constant in a reversible cycle. In a reversible cycle. Okay, or process. So any reversible cycle may be imagined to be divided into large number of Carnot cycles. For each Carnot cycle, total energy of the complete cycle is zero. Therefore, all reversible cycle is total entropy change is zero. So in reversible, there is no change in entropy of the system of the universe. What happens if the entropy during the reversible? Irreversible. What about in case of reversible? What happens in case of reversible? Consider heat engine operating between T1 and T2. T1 and T2 operating between T1 and T2. Then efficiency, we know that efficiency of reversible engine, that is Q1 minus Q2 divided by Q1. Okay, this efficiency is less than that of the reversible engine, correct? I can say that this efficiency less than enough. Okay, so here the efficiency of a reversible engine, that is T1 minus T2 divided by T1, where Ni less than efficiency less than, or then I can say that Q1 minus Q2 divided by Q1 less than T1 minus T2 divided by T1. So in simple, Q1 minus Q2 divided by Q1 less than T1 minus T2 divided by T1. So here I can say that Q2 upon T2 minus Q1 upon T1 is equal to 0. So during the reversible process, the working substance, during an irreversible process, the working substance cannot regain its original state. Therefore, there is change in entropy. However, during the cycle, the source has lost quantity of heat. Okay, and absorbs some quantity of heat there. So in that case, the entropy has increased by amount. It lost some heat to the same. Then I can say that Q2 upon T2 minus Q1 upon T1 is equal to 0. The entropy system increases in reversible. Sorry, this must be greater than. Okay. We know that that the source has lost quantity of heat Q1 and at temperature T1, and its entropy decreases by amount Q1 and T1. And while it is absorbing it, it increases entropy by Q1 upon T2, Q2 upon T2. So this must be greater than 0. Then say that the entropy is increases. Okay, entropy is increases. So I can say that entropy is increases in irreversible process or cycle. So this will be very important thing. So entropy in a natural process, how it will be work. So in a natural process, we know that natural process are irreversible process. Okay, natural process are irreversible process, like natural process. These are the irreversible forces. irreversible process. Then natural process are irreversible process. Then we can say that whenever a natural process is occurs, there is no change in the entropy. So entropy is increased. So entropy increases. So in any natural process, the entropy is increases. As you know that the heat is flowing from the cold body to hot body, the entropy increases. Another we can say the radiations, pendulums, photoning, for all these are the natural processes occur and the entropy is increases. So in irreversible process, the entropy increases. Let's consider condition of heat as an example of natural process. Let a hot body at temperature T1. Let's consider this is a hot body temperature T1 be kept in cold. Let's consider a cold body here at temperature T2. Okay, they will exchange the temperature, or I can say that the temperature is flow from hot body to low body, so from T2 to T1. So I can say that suppose infinitesimal quantity of heat dq flows from hot body to low body. So in this case, the change in entropy must be equal to minus dq upon T1. Okay, the quantity of heat dq is very small. The temperature of the two body remains almost constant. Why it is a negative sign? Because it is decreases. Here it is a irreversible process and the quantity of heat decreases. So this entropy of the hot body and the entropy of the cold body, I can say that dq upon T1, that entropy of the hot body means it is giving temperature to the low body. Sorry, it is accepting from temperature from it is given temperature to the low body. So this is the negative upon T. If ds is the total change in the if total change in the entropy of the whole system of the both bodies divided by ds, then I can say that dq upon T2 minus dq upon T1, and if I take the common dq, T1 minus T2 divided by T1 T2, okay, as T1 greater than T2, and then we get ds is positive. Okay, thus I can say that the entropy in the natural processes is increases. So maximum entropy is get in the natural processes. So entropy is always